Good morning, tensor friends. We're into part two here of our derivation of the Gaussian curvature of the tensor. Part two is about the normal. Who wants to be normal? Anyway, in part one, let's do a quick review. We found these, the basis vectors in our parameterized embedded the space by taking the derivative of the position vector with respect to the coordinates. We found the regular basis vectors of the ambient space, which is the Cartesian distance space. And we defined a new thing called the shift tensor, which was the derivative of the ambient coordinates with respect to the embedded the coordinates. Okay? And from that, we were able to calculate our basis vectors for the embedded the space, and we're going to look at that in a second. And they were this. All right. So let's go to our graphing stuff and take a look at this. So here we have just the Cartesian, the reference to the frame in 3D, right? So the first thing we did was define a vector, and that vector now is parameterized with the spherical, the coordinates. So you can see that it changes from and away from the North Pole with respect to this angle, which we're calling a theta. And it also swings around the equator with this angle, which we're calling phi, right? And the radius then moves it up and down. But for these calculations, we just hold the radius at a constant, the number. All right. So so this space we're looking at here is our ambient space. So we put a point on the end of that vector like that. And then we made a sphere. So now you can see that point move around on this sphere as a function of theta and phi. Okay. So we're interested in the Gaussian, the curvature of this point on this sphere. Now, since all of these points are equal, then once you find one, you have them all in terms of theta and phi. Okay. So on this, at this point on this sphere, we found these relationships for the surface, the basis, the vectors, right? And they look like this. And you see that they're orthogonal. And they also are functions of theta and phi. So they move around with theta and phi, right? Now, we can use these two, the basis of vectors, at this point to define a plane. So this plane is our tangent plane. So this is the tangent plane to that sphere, which is embedded in a three-dimensional space. So it's really starting to add up to what all this stuff is, right? All right. Now, what we want to do in this video is find the product of these two vectors, and that will give us the normal. So the normal will stick straight up from here. So it will be perpendicular to this tangent, the plane. All of this stuff is working our way toward finding the Gaussian, the tensor. All right. So let's go back to our document. And we want to find the normal unit vector normal to the surface of the sphere. So we want to do the product of these two guys. Okay. So in tensor, the calculus, they don't do the product the way we were taught to in linear algebra. So in linear algebra, you've got two vectors. You put them in a matrix. You put your basis vectors down here. You put the first one down, the second one down. In your mind, you cross out this and this, take the determinant of that. Then you cross out this and this. Then you put a negative sign, don't forget. Take the determinant of that. Lastly, you cross out this and this, take the determinant of that, and you get this expression. Well, that's not how they do it. They do it like this. So they write A cross B is equal to epsilon ijk. Epsilon ijk is called the Levi-Civita permutation tensor. Levi-Civita was a student of Ricci. Okay, so they write it ijk and then the ai component, bj component, and then the ek unit vector or whatever the basis of the vector you have. It doesn't have to be a unit vector. In our case, it is because it's just the ijk's. Okay, so the way I do this is I write down a 1, 2, 3 like this. And if I go in the permutation of 1, 2, 3, so clockwise, or 2, 3, 1, or 3, 1, 2, I get a positive sign here. If you go the counterclockwise, 3, 2, 1, 2, 1, 3, or 1, 3, 2, you get a negative sign. So I'll fill in the ijk's each time, right? So 1, 2, 3, I is 1, J is 2, and E is 3. You just keep doing that until you get the format. Then you reduce it down to your vector, your basis vectors, and you get the same answer you would with the way we did it with linear algebra. Now, I'm not going to do this in this video because it is extremely complicated. So what I'm going to do is give you a link down in the description where Professor the Fowler did it on YouTube, and it's from Professor Grinfield, his book, the Tensor Calculus book, which is an excellent book, by the way. And if you really want to know how to do that, it's all there in bloody gore, but it's just beyond the scope of this. It's too much. I know I'm supposed to be doing this in tensor calculus, but I'm going to make that exception because it's just too much. All right. So here's the two equations we got. We just want to cross the product of these. So we write it down the same way, right? Here's our basis vectors. Excuse me. Here's our first, the set. Here's our second set. So we do that the same thing. Cross this out, cross that out. Take this determinant, cross this out, take this determinant, cross this out, take this determinant. And we get this. Then we go and get all of our z's. Here they all are. This was in video number 1, in part 1. We put all that in here and we get this expression. Okay? So this is the cross product of those two vectors. There should be vector signs over here. Oh, sorry. Okay, so now let's go actually look at it. All right, so we've got our tangent plane. We've got our basis, the vectors here, right? Now we want the cross product of those guys. And we have this. You see it? So it is straight up. Now that's the cross the product, but that's not a unit vector. And how do I know that? Because if I change the radius, look, it changes length. Well, that's not a unit vector. They don't change length. That's the definition. So how do you do that? Well, you just divide it by its the magnitude. So if I've got this cross this, divide it by its magnitude, and I get a unit vector. There it is. There's the unit vector. So now if I vary r, you see it's the same length. It doesn't change. Okay, so that's our that's all we're going to do for today. We found the normal, and we're on our way to. Or I said it right here above. It's not the way the tensor calculus. Refer to the link in the description. All right, I'll give you that link. I'll give you the reference to the book too, in case you have the book. All right, so that's all we're going to do for today. Thanks for watching. See you later.